nice Monday. Hopefully not too rough. We had like a huge deluge here in California. It's a lot for Californians. We don't get rain ever. Hi guys. I hope everyone had a nice relaxing weekend. Yes, it's nice to have rain. California definitely needs it. Maybe we'll have less wildfires if we had more rain. Less dry brush. Ooh, yeah. I love rainy days. I used to love going to get pho on rainy days. Oh, those are the best. Nice warm soup. Yes, nice and cozy. Stay at home. Ooh, shabu shabu sounds good too. Sorry, I just ate lunch, so I'm okay. I can make pho. What are you talking about? I won't treat you guys to pho. I'll make it. I'm Vietnamese. If only you guys are all here. But yes, we make our own pho. Actually, since the pandemic, we started making every kind of food that we wanted. Like everything that we were craving. Yeah, it was awesome. Like we were making like Chilean sea bass with miso, like glaze. We did, yeah, we fancy. We go out when we're lazy to cook, but majority of the time, yeah, that happens too, right? Sometimes you just feel uninspired to make something because you're cooking all the time. Oh yeah, sushi. Sushi is delicious. Like we do sushi nights too. Uh yeah, like if like you guys are on my Facebook, like half the pictures are of my son, the other half are of food. I've been trying to like document everything that we've made over the pandemic. It was actually kind of nice. So yes, definitely a newfound thing. I feel like that's also why restaurants are hurting now because majority of people realize that hey, it's actually not that hard to cook food. Yes. Oh yeah, learning proper camera angles. Hey, there's an AI for that, Jonathan. If you actually look at Arsenal 2, there's an AI you can put on your camera now, and it'll actually give you the proper settings, the proper ISO, the proper like shutter speed and everything. Yeah, it's called Arsenal 2. It's pretty crazy. I just got it for my wife for her birthday. It's so awesome. So we can take like pictures of like time lapse of the night skies. You know those like really cool shots that you see people take all the time. Yeah. So it does it automatically. You just press a button. The AI calculates everything out. It calculates the speed at which the stars are moving, and then it does a little slow time lapse of it, and it's so cool. It looks like a nice like pan across the sky. Very, very, very cool. So pretty cool thing. It's on Kickstarter, and I think it's like really, really cool. I thought it was awesome, but it only works with those nice fancy cameras. So if you have a nice fancy camera, then it's totally worth it. So bringing that back, since we're talking about cameras and lights and all that stuff today, we're talking about waves. So let's learn some basic. Yeah, good segue. Thank you. We're bringing it back. But yes, rainy days make me think of like warm, cozy food. But yes, bringing it back to waves. So today we're going to talk about waves and certain wave mechanics that we need to know. The types of waves, transverse waves, longitudinal waves. I have two cool demo videos to show you how we can get standing waves for both the transverse and a longitudinal wave. And yeah, I think like it's nice to see it in action as opposed to just thinking about it as like a visual of what like people call a wave, you know? Which by the way is a sinusoidal wave or a sinusoidal like up and down curve, right? That we always like model it as. But it's nice to see what is actually being done there. Hopefully Amon's internet stabilizes a little bit and they can hang out for us. So let's talk about waves. So for mechanical waves, The only one non-mechanical wave that we're going to talk about is our electromagnetic wave, which we're going to talk about in our light and optics lecture. So mechanical waves transmit energy and momentum through a medium. So it's going to give you energy and momentum. So every wave that we talk about, from your wave on a string to electromagnetic waves to sound waves, they're all transmitting some form of energy and some form of momentum, okay? There are two types of waves. The first type of wave that we need to know is the transverse wave. Oh, we had a question come in. Can we define momentum? Okay, so momentum is inertia in motion. So if you think of an object having inertia, like some kind of mass, and we put that mass in motion, that's momentum. I don't see how they cannot have momentum, because if you think about it, how do you think chemical reactions happen? Do they just magically come close to each other and not hit each other, and then it just like they could form bonds? No, it's collisions. So I think it's funny that because you think about every type of chemical reaction that we talk about, whether it's biological or physical, it's some type of collision, right? And so in order to have collisions, you need to talk about momentum, because every object is in a mass in motion. So I always think it's funny, like whoever was writing the MCAT and decided to cut momentum, and I was like, well, you just cut the basis of every chemical reaction that's out there, right? Because why do we think we have to wait for so long for chemistry to happen in all those chem labs that you guys did, right? Where you sat in chem labs for hours and hours and hours. You're waiting for these molecules to collide with each other. Yes, one less thing to worry about. But if someone wants to know, I'm going to provide the answers to them. Okay? So you don't have to know exactly what momentum is. You just know that it's inertia in motion, right? So it's a mass with some velocity, basically. So what a wave does is it pushes mass, and you'll see it, right? So we'll talk about like the types of waves. So let's go over the types of waves. The first type of wave is what we call a transverse wave. Transverse. For the transverse wave, the movement of material is perpendicular it doesn't transfer matter, it moves it out of the way. So the wave will disturb matter that's there. It doesn't actually move matter like you're not physically moving molecules, but it's going to move it out of the way. Okay? So like if you think of like if you were in the water in the ocean, right? When the ocean wave comes in, you just move up and down, right? Just like if you think about it, if you don't go in the water and like you don't surf, you don't swim, you just think of the buoys. What do the buoys do? They go up and down and up and down. They don't actually get moved closer to the land, they just move up and down. Okay? Yep. So this is what we're talking about. The movement of material is perpendicular to wave propagation. So for the example of that waves on the water surface, your motion is moving up and down, but the wave is propagating towards the shore, right? So it's perpendicular to the direction of the movement of the material in the medium that you're in. So there's two waves that you can think of. The MCAT likes to test you on probably both of these. Both of these are what we call mechanical waves. This is a wave on a string. This is the one we're going to talk about the most today. And the second one I just brought up was the wave on the water surface, like the ocean waves. or those man-made waves that you have at like those like water theme parks, like Raging Waters or Manteca water slides, close to here in California. I'm sure you guys have something like that wherever you are. So both of these are what we call considered mechanical waves. So mechanical waves need a medium to propagate. So they need some type of medium. So medium means some type of material at which it's going to move in, right? So a wave in a string, a wave on the water surface, and sound waves, which are transverse waves, are what we call mechanical waves. They need a medium in which they're going to propagate through. The third type of wave is the electromagnetic wave. For the electromagnetic wave, it does not need a medium. So if you think about it, light propagates through space. We know that, right? Because the sunlight from the sun gets here to Earth. There is no medium in space, right? Right? The definition of space is a vacuum, right? The lack thereof of a medium. So we know that electromagnetic waves travel without that need for a medium. So all of these waves still carry with it energy and momentum, right, when they're moving. So just like the waves on the water surface, imagine that you tied a string to your door, and in order to get a wave to propagate, how do you have to move your arm? You move your arm up and down, just like the buoy on the water surface, right? So if you move your arm up and down, you create a wave that moves towards your doorknob, right? So the movement of material is perpendicular to wave propagation. Same thing with the electromagnetic wave. So what an electromagnetic wave does, so imagine if this was your chemical bond and these are the two atoms, it moves these things up and down. It vibrates it up and down in your atomic or substrate structure, okay? So it causes the molecules to vibrate up and down, okay? So that's what electromagnetic waves do. And when we talk about waves getting things to resonate, it's vibrating perfectly so that when the wave hits, just as that one thing relaxes and comes back to normal, and then another wave hits and another wave hits, and it keeps on doing it, and eventually it builds up, right? So when we get to what we call resonant frequency for a type of material, you can get that material to break, like glass, right? You hear about that example all the time where an opera singer or someone with a nice melodic voice can sing at a pitch that's resonating at the same frequency that the atoms of that substrate or structure move at, that they'll cause the molecules to eventually increase in amplitude in terms of the waves compounding, and it will cause it to break. We'll look at videos on all of these things in a little bit so that you can actually see it. And I think like you can talk about this in theory, but when you see it in action, it's super cool, okay? When it comes to electromagnetic waves, does the vibration occur on the object we're looking at in order to produce the color we see, or does the vibration occur in our eyes? For electromagnetic waves, what we see is so Michaela, so when we're thinking about what we see as color for the object that we're looking at, it's usually reflected color and absorbed color. So remember how we talked about absorption and emission way back when, with the electrons being able to absorb energy and get the electrons to jump and they give off photons of light, right? So what we see is reflected light. So when an object is not radiating or iridescent, it's not giving off its own light, right? Or electromagnetic radiation. So what we see is reflected light. So, right, the best way to think about it is, if you turn off the lights in the room, will that object still give off color? So if it doesn't, then what we see from that object is reflected color. So when light hits an object, it absorbs everything but the color that it's reflecting, okay? So when we think of what we see in the limited spectrum of the visible spectrum. And within your visible spectrum, we see the colors of the rainbow, right? This is your Roy G. Biv, right? Red, orange, yellow, green, blue, and violet. So when colors or materials or substrates, they can absorb their vibration frequency a certain color, right? And so that's a certain energy, right? Because the energy of a certain wave is simply Planck's constant times its frequency. And when we look at the electromagnetic wave in a little bit, it'll make sense because each color has associated with its own different frequency. And so each frequency will be this resonating frequency at which these atoms can vibrate back and forth. Okay? So what we see is what's being reflected. Okay? So if you think about your shirt color, your table color, yeah, it's whatever's absorbed, we get to see the opposite because that's probably what's going to get reflected. So that's your color wheel that Tiffany's talking about. Might not be obviously clear, Tiffany, if she has no idea what a color wheel is. So what Tiffany's saying is, if you think about it, this is your typical color wheel. Red, orange, yellow, green, blue, violet. Yeah. Okay. Cool. Okay, good. Everyone knows. I think of transverse because it's really easy. So I remember ocean waves, right? Because I love to swim. So when I think of a transverse, it's always going moving up and down, like the Trans America building, it's really tall, right? So it's always vertical in terms of its motion. So that's how I remember transverse as being perpendicular to whatever the direction of a wave is, because I assume all waves are coming at. Yeah, and I remember longitudinal is long, which means it's going to be stretched out. So I think of it as an accordion. Does that work for you, Amanda? It might not. So that's how I think about it. So everyone's good with the color wheel because Tiffany brought it up. I was like, oh, some people might not know what that is. I remember for the longest time I had no idea what reflected color versus emitted color was, and I didn't know the difference either. So I mean, this is all stuff that you pick up and learn along the way. I felt like being a teacher, I learned it even better than when I was a student. So the first type of wave, transverse waves. We will go over electromagnetic waves in our light and optics lecture. Okay, so we'll go over further about electromagnetic waves. We'll go over applications of so we'll go over applications of light and optics today, dealing with Young's modulus and not Young's modulus, Young's double slit experiments. Okay, but that's the only thing. We'll go further about electromagnetic waves on during the light and optics lecture. Okay. So both the wave on a string and a wave on a water surface are mechanical waves. The second type of wave that we need to know is the longitudinal wave. For longitudinal wave, the movement of material is parallel to wave propagation. And the perfect example of a longitudinal wave, for the one that you're going to need to know, we're going to deal with it during the sound and Doppler lecture. It's a sound wave. And for the sound wave, if you think about it, so think about your speaker. Really what's happening is a spring with a mass here that bobs back and forth, and it creates waves that move parallel to the wave direction. So what it does is it compresses the medium into regions of high pressure and regions of low pressure. So they always draw it like an actual sinusoidal wave moving from a source like so. But really what's happening is it's getting compressed into regions of high pressure and low pressure, high pressure and low pressure. And we'll look at a video on what that is in a second. At the end, after I go through all the material that you guys need to know, and then we'll look at the videos and look at the applications, okay? So transverse wave, longitudinal wave, movement of material is perpendicular for transverse, and longitudinal, lengthwise or long, is parallel, okay? For waves, let's look at some wave characteristics. So for the wave characteristics, so typical sinusoid wave, there are points of interest that we care about. The peaks, the crests, and the troughs. These are called antinodes. And the 0 points, these are called nodes. Okay. The distance between every other node or every other antinode is called a wavelength. The units are in meters, and it's symbolized by the Greek letter lowercase lambda. Everywhere on this wave is moving with a certain velocity, and that velocity is simply the wavelength times the frequency. Frequency we discussed last week already when we talked about periodic motion. So the units are meters times inverse seconds, still in meters per second. Okay. So know your speed of a wave. It's simply some wavelength times some frequency. So this is a typical ideal wave, right? Where everything is nice, uniform, same peaks, same crests and troughs through all the way throughout. Oh, you think of a node? Anti are like nodes. Nodes are just 0 points, and anti are the maximum and mins, right? The next thing we need to know is a wave on a string. Thank you. The speed of a wave on a string is simply the square root of the elastic property of that string over the inertial property of that string. So mu is some mass per unit length. T is your tension. This is linear mass density. Okay. Realize that frequency is dependent on the energy source that is supplying the wave. Square root? This is v. Oh, you want to know what it is? It's just velocity. Velocity of the wave on a string. So remember, frequency depends on the energy source. Like think about like that rope on a string and you're trying to like get it on the door and try to create waves. How fast you move your arm is how much energy you're supplying, right? So just keep that in mind. So frequency depends on the energy source, while wavelength depends on the medium that you're traveling through. So as this wave moves through that medium, different mediums will have different wavelengths. Because in certain mediums, a wave will travel faster or slower, right? Think of sound. Sound travels faster in a liquid medium like water than in an air medium like gas, right? Or a gas medium like air, sorry. Vice versa. So, need to know the speed of a wave on a string. This equation has come up quite a bit. So, the way the MCAT likes to test this, so we need to look at what happens when a wave hits a fixed point or if it's open. So think of an oscillator. That's creating a general waveform. I'm going to approximate it as concave up to make it easier. I mean, concave down or just one hump to represent one wave. So we're going to talk about things in constructive and destructive interference to make it easier to see. So I don't have to draw both halves. So when we're sending a wave down, a wave on a string, the first case is if the string is tied. So if that wave comes in and the string is tied, and so i.e. it's not free to move or it's running into something more massively dense. Yes, an oscillator is just a machine that produces waves. I used to say vibrator, but then people would giggle and be childish. So oscillator sounds less other things. So yes, it oscillates. It moves it up and down. So as that wave hits, it's not free to move. So when it comes back half out of phase. So the reflected wave is half out of phase or 180 degrees out of phase. So that's one case. The other case, ideally, you're not losing energy, but in real life, we all know that's not true. So in ideal physics world, they're saying, no, we don't lose energy for your MCAT. But in the real world, we all know that it's going to lose some energy, right? But for the MCAT, I think they're maintaining that the wave bounces back perfectly with the same amplitude in the reverse direction. Good questions. Ideal. Yes. So the other case is if that wave approaches and, sorry, it's open on the other end. So what ends up happening, this wave, this string can then go up and then come back down, and it'll come back down in phase. So the open end simulates something with no resistance or no mass density. It's not running into something. And the closed, the tied end simulates something that it's running into infinite mass density or something that's so big or some density different. Yeah, density-wise different from what it actually is for the string, that it's causing it to be immobile or not be able to move. Okay? So these are the two ideal cases, right, of the tied and the open end. So one's out of phase, one's in phase when it comes back. Okay? So the way the MCAT likes to look at these, they have varying strings of different mass densities. So obviously you can see that mu2, the linear mass density of mu2 is going to be greater than mu1. And it simply says that if mu1 is equivalent to mu2, then most of the energy is transmitted. And if mu1 is way less than mu2, then most of the energy is reflected. Okay? So if we're sending a wave down the first string and it's running into something that's more dense than it, what do you expect that wave to do on the thin string versus the rope that it's connected to? So majority of the energy will come back, maybe less of a hump, and some of it will be transmitted. Very little, right? I think of this as me running into like LeBron James, right? I'm a small little Asian guy. Okay, I'm not that small, but enough to play. So if I'm running into LeBron, what's going to happen? I'm going to go bouncing back. LeBron goes, huh, right? He moves very little. The other case, now if LeBron comes coming down, something that's more massively dense. Actually, yeah, kind of like Space Jam. Though the original Space Jam with Michael Jordan is so much better. Sorry. So if LeBron's coming down the lane, yes, Jordan over LeBron. Sorry for those of you guys who are LeBron fans. So if LeBron's coming down the lane, what's going to happen? LeBron just runs through me, right? So if the more dense string is approaching the less dense string, this interaction between the two acts like an open case, right? Where most of that energy is going to be transmitted through and some of it is reflected back. But since it's more massive, it does what it wants. It's reflected in phase as opposed to being out of phase. So if we think about the junction, so someone was wondering like what's happening realistically. If we're looking at the junction of what's right here, so when you're going from less dense to more dense, it's behaving like if you're running into like that tied string case. Okay? And if you're running from more dense to less dense, which is right here, it's behaving like the open string case where it can just freely move, right? Because the mass of this string is more dense, more massive, and since a wave carries energy and momentum associated with that mass, it's going to do whatever it wants to do, right? So that's why this thing comes back. This is in phase. And since it's running into something more dense, this is why this is out of phase. It does come up a fair amount because if you think about this concept that I'm trying to teach you between being in phase and out of phase is every interference thing that you're going to talk about. Whether it's Young's double slit experiment, whether it's thin film interference, whether it is sound wave or noise canceling headphones and things canceling out, these are all things that come into play, right? So that's the reason why I'm going over this whole transmitted versus reflected type of system, because this comes up quite often. But if you can understand the simple string example, the same thing is happening when we're talking about light, when we're talking about sound as well, because all those things are still considered just waves, right? So when we talk about light being reflected, right, it's the same thing happening with this type of reflection, because still remember, light waves or electromagnetic waves are your transverse type of waves. Does that answer the question for the person that was asking it also anonymously? Okay. So remember what we just talked about before with the tied end case? So when it's tied, imagine it's running into something that's more dense, so dense that it can't move it. So then the string, in order to preserve that energy that it has to just invert itself and come back half out of phase. And the open case, since the string is so dense, it can do what it wants. It's just going to move up and down and then come back in phase like it normally did. Do you understand this example? Sorry. Sounds good. Thank you. Okay, so now with this understanding, thank you. So now with that understanding, we can talk about interference, right? So things can come back in phase and come back out of phase. And so with that knowledge, we can talk about interference. So with interference, is two waves coming together at a specific point in space and time. So they have to come there at a specific point in space and time, okay? So interference. So when we have two waves, there are two types of interference. The first is constructive interference, and the second is destructive interference. So with constructive interference, this is when two waves approach each other in phase with one another. And when they overlap, you get twice the area under the curve. So the graph looks twice as big. And after they pass each other, we'll call this V1, we'll call this V2, they'll behave as though they never saw each other. Still V1, still V2, still same amplitude that they had before. So this constructive interference that we're talking about only occurs at a specific point in space and time, right? If it's on one string, it's only when they cross and overlap with each other, right? But this could be for sound waves. You have one sound wave going in one direction and one sound wave going in another direction. Constructive interference Okay, so someone wanted to write a simplified definition for them. Okay. Is constructive is the addition of two waves that are in phase. And destructive interference is the subtraction of two waves that are out of phase. Realistically, we're just adding them, right? Except one's opposite of the other. So for the destructive interference, one's in phase and the other one's out of phase. So one will have positive area under the curve, one will have negative area under the curve. Okay. So when they overlap each other, there is no type of wave. Correct. So the difference between constructive and destructive is whether they're in phase or not, which is why it was important that we talked about how these waves can become out of phase with each other. Does that make sense? When it runs into something more massively dense, it comes back out of phase. If it runs in something that's less dense, and we'll talk about this with light when we talk about reflection and refraction, actually more reflection. Yeah. Oh, so with beats are both destructive and constructive. It's interesting. We'll talk about that too. And we'll talk about beat and beat frequency in a little bit. So I'm going to talk about it right after I talk about this, the last slide that I was on. Okay, let me finish this up. And then after they pass each other, yeah, they're going to move with the same. So we'll call this V1, V2. This is still V2. This is still V1. Same amplitude, now just moving in opposite directions. Okay. Cool. So with beat frequency, if you guys open up your books onto that section 4, there should be a nice graph of beat frequency near the end. It's in the periodic motion and waves. Yes, it's on page 153. Sorry, I'm going to turn on my camera real quick. So on page 153, there is your one wave. Here's another wave with a relatively higher frequency. And beat frequency is the constructive and destructive interference. So where you hear the loud part of the beat is the constructive interference, and where you hear the soft part is the destructive interference. So a beat frequency actually has both. And this occurs when you play musical instruments or have two sounds or two waves of close frequencies with each other. They form and combine to form a beat frequency, or a constructive and destructive portion of the wave that forms a new wave. Does that make sense? If it's solely constructive, you only get loud. And solely destructive, you'll hear nothing. Right? Beat would actually hear a continuous beat, right? I don't know how tides would make a difference. I would think the tides would have to deal with gravitational pull, right? So I don't see how that changes the waves of a sound. Remember that the waves of certain sounds come from the energy source. Maybe low batteries might be a case, but I don't see. But I don't see how the tides would make a difference in terms of gravitational pull. Yes, yes. If you have two waves of different amplitudes, right? Isn't that what destructive is? One's a positive amplitude and one's a negative amplitude, and then when you combine them, that's just zero. Does that answer your question? So then you'll get a beat frequency of like 2. Yeah. So if they're so beat frequency is just the difference in the two frequencies. Yes. And its absolute value. Doesn't matter if it's positive or negative. But that's how you're going to generate that beat frequency. It's just the difference in the relative frequencies that you have in between. So I don't know if you guys know this, but Patricio like plays in a salsa band. So when he plays and then I play, then the difference in the relative frequencies at which we're banging our drums will create a beat, right? All right. I wish he does it professionally. I do it for fun on the side. I'm not at the level Patricio's at. he's amazing. He gets gigs everywhere. So it was his hobby and then it became his job, and it's pretty awesome. Patricio's like a really cool dude. Like the more you guys get to know him, he probably doesn't like to share that stuff about himself, but I'm like, that's a really cool thing. Like I went because he would invite me to go to all his salsa dance clubs things that he does all the time when I was like we were like studying together and all that stuff. Correct. So the only way two waves would be constructive or double in amplitude if they were the same size to start. But if they were, one was 4 in amplitude and the other was 6, so when they convolve or overlap with one another, then it'll be an amplitude of 10. Does that make sense? You're literally just adding amplitudes. It's way harder than that in real life, right? But for your MCAT, that's literally what you're doing. No, so frequency and amplitude are different. So amplitude tells you how big this is, right? If this was a height of 4 and this was a height of 6, when they overlap with each other, right? If they were approaching each other, then you'll get something that's a height of 10. Amplitude tells you the size of how loud it is, how bright it is, right? Frequency tells you how often you hear it or see it. That's the difference, right? So when we talk about it, we talk about amplitude as what we call intensity. How intense is it, right? When we talk about frequency, we talk about how many cycles do we see per second or how many cycles do we hear per second, right? So with those new LCD screens, right, you're getting like whatever, like close to 240 hertz. That's 240 frames a second, right? If you go back in some of the older TVs, you can actually see it go down. There's like a refresh frame and you'll see the line go. And that's like maybe like, 6 frames per second, right? So the reason why images seem so clear now in all the new technology we just have a higher refresh rate. So there's less gaps so that the eye can actually distinguish the difference between things. Okay, so be clear, amplitude and frequency are two separate things. They're not the same. Okay? So with that, let's now talk about standing waves. So with standing waves, these are waves on a string where the string is fixed on either end. So they're fixed or tied. And if we pluck it and we give it enough energy to generate a wave, the longest possible wave that we can form looks something like this. And realistically, one wave is going this way, one wave is coming back, okay? But it's doing it so fast that it looks like it's staying still. Yeah, like a guitar. Yeah, or every stringed instrument that you think of, right? Cello, guitar, violin, anything, right? Any of the stringed instruments, you have a neck and a bridge where it's fixed, and then you're just plucking it in between. You can, like, you think about a guitar, you're not plucking it at the center of the string, right? Think of the length of the neck of your guitar, and then where the acoustic hole is to reverberate the sound into your guitar. You're not plucking it there. Someone asked if would they ever pluck the string from a spot not in the center? Ideally, the MCAT does everything in an ideal case, so they always pluck it like roughly from the center. Oh yeah, the definition of a standing wave is it's an actual traveling wave that, you know, like you think of a wave moving down a string, except since it's fixed on either end, it looks like it's staying still. So standing waves are moving when we do it in time lapse, right? And I'll show you a video in a second. They're still moving forwards and back, forwards and back, forwards and back, except when it's done really fast, it looks like it's staying completely still. Okay? And we'll go over a video to show you that. Yep, that's what I'm going to do in a second, Sophie. Right? Because seeing is believing. Okay, so since we know that one wavelength is going from node to node or every other node, we're going from one node to the next node. So how much of a wavelength do we have here if this is some length L? So we're going from one node to the next node. So we have what? And this whole thing was one wavelength. So from here to here was lambda, but to go from red to red is what? Just half of that, right? Half of the wavelength. So L is equal to 1/2 lambda. So lambda, the wavelength, is equal to 2L. And since this is the longest wavelength available, no, for the first harmonic, it's halved. So if you put more energy in, you can get different standing waves. You'll see in a second. So the longest possible wavelength that you can have, this is the lowest energy that you put in, by the way, is called the fundamental, or commonly referred to as the first harmonic. Now, if you put in more energy, you can get that wave to form. So one is going this way, the dash one is going the reverse direction. So this is the first harmonic. For the second one, this is one full wavelength, so lambda is equal to L. This is referred to as the second harmonic, or the first overtone. The next one look like so. Okay. This will be the third harmonic. So L is equal to how many wavelengths we have here? So this is 1.5, right? Because you think about how many nodes we have. We have 1, 2, 3, 4. 1, 2, 3, 4. So this was our 1 wavelength. And this is the extra half of a wavelength right here. So this is 3/2 lambda. So lambda is 2/3 L. This is commonly referred to as the third harmonic or the second overtone. So, given any harmonic, what is the trend that we get? And given from that, we should be able to figure out the frequency. First harmonic was L, 2L, second harmonic was L, third harmonic was 2L over 3. Jonathan got it. The wavelength is simply 2L divided by the harmonic number. L is the length of the string. Does that make sense? Cool. And then we know that speed is equal to lambda times frequency. So frequency is speed divided by lambda, which then becomes NV all over 2L. So given any harmonic number where N is equal to your harmonic number, we can then find the wavelength and the frequency of that standing wave. Any questions on that? Cool. Just want to make sure. So I'm going to let you guys see a video of this wave in action to show you that I'm not lying. It's still moving, but when we do it in really fast, like really high frequencies, it appears to be staying completely still. Hence why the name standing waves. But when we slow it down into freeze or slow frame motion, we can actually see that wave oscillating back and forth, back and forth, back and forth. Okay. I'm going to have to clear all the whiteboard to do that, to share with you the video. So if there's any questions that you need to go back to a previous slide, please ask now or forever hold your peace. If not, I can rewrite it again. We still have a lot of time. Okay.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just
Doesn't it remind you of like all your physics teachers
up and
back
down
in high school?
at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving
Transverse
up
nature.
and down. And we'll see that in a
So
second
here's the
with
high
high-speed
speed.
camera.
So it's going forward, back, forward, back, forward, back, forward, back. Do you see?
So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, this is a node, and the middle's a node. So we have 3 nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump rope. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was that around 25.5. And there we go.
So this is what I was talking about, how they're traveling waves,
So
but they
that's the
appear like they're
third
staying
harmonic.
still, right?
How many wavelengths is this? Well, it's 1 and a half. 1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high speed camera and verify for yourself that it is 1 and 1/2 wavelengths.
So if we freeze frame at any one point, you can see that there's 1 wavelength and a half clearly now.
So again, third harmonic, 1.5 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
Yeah, we just went through all the derivations and calculations. So yes, transverse. These are all transverse waves, right? Waves on a string was a transverse. A full wave is a full wavelength. So when I did it, I gave you what a full wavelength was. Go back and look at your wave characteristics, Michaela. Yes, seeing in video is huge, Aditya, as opposed to seeing it like in a textbook. So every other node or every other antinode is 1 wavelength. Correct. All waves on strings are transverse waves. Yes. Always, always, always. Why? Because the movement of material is perpendicular to wave propagation. Okay? So now let's take a look at a longitudinal wave and how it's different as opposed to the transverse wave. Yes, so you can do every other antinode or every other node, Michaela. Though that's 1 wavelength. Right? Because if you think about it here, you can either look at it from a cosine or sine perspective, right? So if you're doing every other node, that's a sine graph, right? That's one period of a sine graph or one cycle, right? Or you can do every other antinode, that's your cosine graph, right? That's every other antinode. This is your cosine graph, this is your sine graph. Now, if you keep on graphing it, they kind of blend in with each other. They look the same. So where you choose to start it and where you choose to end it will determine what your cycle is. Every other node or every other antinode, Alexandra. So these are the nodes. So every other node, we're skipping that. That's one cycle. Every other antinode. Does that make sense? So this is one wavelength. This is one wavelength. Right? So in a continuous wave, right? Imagine like you have a continuous wave. It doesn't really stop, right? It just keeps on going like this. As long as you're providing energy, like your speakers, it's continually playing. That sound is going to be continually playing, right? So you have to know when is what is called one wavelength or what is one cycle, right? And frequency is just how many cycles we get per second. That's it. Does that make sense? For those who are still confused. Awesome, awesome. Cool. So now let's take a look at a longitudinal wave. Let me cue it up real quick. Okay. Super cool video. Now you get to see a longitudinal wave as opposed to the transverse wave that we just saw. And we'll go and look at another video after explain what's happening inside the video or what's happening inside the tube. So here's the demonstration. So what the guy has here is a PVC pipe wrapped with aluminum foil on the inside. He's put propane gas inside and he's poked holes on the top at equal increments. So what he's going to do is light it, which is really cool, right? Because you get to play with fire. And I was like, if I was a kid and I had to go back, this would be the physics experiment that I do for like, you know, third, second grade science fair or something like that. But what it does is it gives you a way to visualize sound with that propane gas, the medium.
Let's do a classic physics experiment called the Rubens tube. Now, I really want to bring it down, but it involves open flames, and some people have issues with open flames. So, what we have here is a length of PVC pipe, has about 100 or so holes drilled at half-inch increments, got some foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of this 2-inch tube. On that side, we've got some lab tubing leading to some propane. So let's fire it up and see what it does. Alright, as you can see, we got some nice standing flames, a little bit of oscillation from the vibrations in the hose. Let's throw some sound in there and see what happens. Let's start with a 449 hertz frequency.
Standing waves.
As you can see, this sets up a standing wave, and we can see, well, the emerging sine curve that represents sound. What happens here is we're having the sound compressing here and not compressing here. The lower pressure here allows more gas to escape into the atmosphere, shaping the sound curve. Now, if we change the frequency, we can see each time we set up a standing wave, we get that sine curve. Higher the frequency, the more waves. Now let's throw some music at this. How about some Dave Brubeck? Now we have real life sound visualization with 5. The debut rec isn't terribly energetic, so let's try something a little more energetic.
So what you guys can see here is super cool sound visualization, right? who needs a baking soda volcano? That would be way cooler, right? Think about this at like Burning Man, and they already do it. Right? Because if you think about it, it's real life sound visualization, right? You're looking at all the waves of sound coming from your music, and it's showing the waves coming through. Now I have another video to show you what's happening inside of the tube. So to show you how it has a longitudinal nature. So where is it? I believe it's this one. Sorry, gotta get through this ad. I'll reshare the screen in a second once I queue it up. Okay, so this video has what's exactly happening inside of the sound tube, where the longitudinal nature, where the movement of material is parallel to wave propagation. So you didn't clearly see that with the Rubens tube, but this one has an animation that shows you what's happening on the gas molecules inside. And this guy made a 2D Rubens tube where sound is coming in from two ends, and then he makes an array in which the sound is getting visualized. The grad student.
Now you may have seen a Rubens tube before. That's basically a pipe with a bunch of holes in it, and you pump in a flammable gas and light it on fire. So you basically create a row of Bunsen burners. What's really cool is to play some sounds into the tube, and you can actually set up standing waves. Whoa. That is, there are areas, there are patterns of the vibration of the air where there's a lot of vibration in some parts and not very much vibration in other parts.
So
now that affects the flow rate of the gas inside that tube into the atmosphere, and so it affects the height of those flames. So basically you can visualize the standing wave pattern. I'm currently in Denmark with a team of physics
molecules coming out. That other guys announced it. Can you hear me? Okay, so sorry. You can hear me now because the video stopped. So what was happening is during the video, when the molecules were moving back and forth, which you saw, like an accordion, the places where the molecules moved the least, that's where there was less fire coming out from the top, right? And where the molecules move the most, that's where the most fire comes out, right? So, but you notice that the movement of material for the gases inside that tube are parallel. So it's like an accordion going squishing, then moving, then squishing, then moving. Regions of high pressure, regions of low pressure, regions of high pressure, regions of low pressure, right? Literally. You guys are really good with the puns, man. Yeah, literally, Amanda, I totally agree. Super cool to see real life visualization of both transverse waves and longitudinal waves to show you exactly how those waves are causing the molecules to move, right? That parallel nature and for the longitudinal waves, and the perpendicular nature for the wave on a string moving up and down, up and down, up and down, like we talked about, okay? Now that we've discussed that, let's talk about the electromagnetic wave and light real quick. And then we can do some practice questions, okay? So let's look at the electromagnetic wave or the electromagnetic spectrum. Yeah, if I had to go back, that'd be my third grade science project. How cool would you be doing that at like a science fair? And you get to play whatever music you want that's energetic. That'd be so awesome. Literally fire. Okay, so yeah, no adult supervision, right? You're stuck at those science fair basically by yourself. My parents were always working, and so they were never there anyway. So we have AM radio waves. We have FM TV waves. Then you got your microwaves, infrared. There's this thin sliver. This is the visible spectrum. Then you have UV, X-rays, and then gamma rays. And then there's something greater called cosmic galactic rays, but at that level of energy, we would get nuked. So these are all things you guys use pretty much every day, except the high-end stuff, right? The X-rays and the gamma rays. So in terms of the electromagnetic spectrum, frequency for the AM waves around 10 to the 6th, the FM TV waves 10 to the 9th, microwaves 10 to 11th. It's around 10 to the 14th for your infrared. For your visible spectrum of the Roy G. Biv, it varies between 4 times 10 to the 14th to 7 times 10 to the 14th. UV rays around 10 to the 17th, X-rays around 10 to the 19th, and gamma rays around 10 to the 21st. Realize that speed of light is a constant. It's 3 times 10 to the 8th meters per second, and that's still equal to some wavelength times frequency. So to find the wavelength, all you're doing is taking the inverse or the reciprocal of that frequency, and then you multiply it to your speed of light. It's in light and optics. C is the speed of light. This was not in that wave section, but it's still part of waves. So I just want to be able to discuss this now because we might not have time, because if I'm discussing all the different things associated with light later, I might not have time. It's good to know that it's increasing from left to right. Okay. The only ones you need to remember are the ones from the visible spectrum. That's the ranges. Yes, the order matters, right? So you're going from lower energy to higher energy. Because remember, the energy equation is Planck's constant times your frequency, or Planck's constant times nu. Nu is also another way of writing frequency. F and nu are the same thing. So it looks like curly V. Okay. But it's just frequency. And H here is what we call Planck's constant. It's a constant number. You don't need to know it now. We'll go over it when we talk about light and optics a little bit more. But we do need to know the relative order. And so what we notice is that every type of electromagnetic wave has some energy associated with it, right? So when that energy of that wave hits, some of it can be absorbed, some of it is reflected, right? And so like the wave on a string, even because it's still transverse, when that wave is reflected, it can come back in phase or out of phase, right? Depending on if the medium that we're going from to the new medium is going to be greater versus less, and it'll be reflected if it's going half out of phase, if it's going from less to greater, okay? So just keep that in mind. So the same principle that we talked about for that wave on a string, we're going to come back and talk about it again, okay? So with respect to light, we're going to talk about Young's double slit experiment. And the reason that we care about Young's double slit experiment it is the first proof that light behaves both as a particle and a wave. So before that, all that absorption and emission stuff that we talked about, that's light behaving like a particle, right? Absorbance and then emitting photons of light. Those are lights behaving like particles, right? So what happens with Young's double slit experiment is we're pushing. So there's 3 criteria that you need to know for Young's double slit experiment. The first is that the waves are monochromatic. That means one wavelength. Yes, I will do that. Apologies. That was not conveyed. Thank you. I'll get it to Josh so that he tells you guys. Diffraction. Let me rewrite it better. Diffraction. DIF fraction. And diffraction is just simply bending of light through a small opening. Like you're pushing light through. We'll talk about that in a second. The second thing that we need to know about Young's double slit experiment is that the waves are coherent. That just means that the waves are continuous, they're not broken up, and they have relatively the same wavelength and amplitude at every given point. And last but not least, the waves have the same polarization. So, with Young's double slit experiment, so here's the double slit. 2 things are happening. The first part is diffraction. So diffraction happens at the slits. Diffraction happening at the slit is you're putting a wavelength that's fairly large through a small opening. There's 2 waves coming in. Okay? It's going through that opening. So what ends up happening is that giant wavelength tries to fit through that opening, and it comes out like this. So it comes out in all different directions, and it bends in. So it's kind of like the wave on the water surface when you have a jetty, right? If you ever seen the wave breakers on the shoreline, they have it all the time at like those beach resorts to keep all the high waves from entering into the nice little like alcoves that they put in, right? This is what's happening, right? And it creates that ripple effect of that wave coming in. So that's what diffraction is. Fitting a large wave through a small opening and getting that effect. And then on this side, you still get that same thing here. Perfect. Will do. Yes. When I change, I always ask people, do you have any more questions? Usually that's the cue to screenshot the slide before I move on. So diffraction is the bending of light through a small opening. So the points of key interest that we have here, the distance between the slit is some distance d. And then on the other end, we have a detector screen. And what you end up getting is we're comparing the distance from one opening to the distance from the other opening. Okay. So if that distance between the two, what we call the path length, is equal to 1/2 times m plus 1/2. Sorry, lambda times m plus 1/2 is equal to d sine of theta. So if that path length is 1/2 out of phase, this is going to give you destructive interference. And if it's constructive, it's just lambda m is equal to d sine theta. That's the path length. This is going to be considered constructive interference. And so that path length is the difference. So delta is the difference between the blue wavelength and the green wavelength. So if it's a whole integer multiple of the wavelengths, then it's going to be constructive. So let's say, this is 10, sorry, this was 10 wavelengths to get here, and this was 11 wavelengths to get here. Given that the wavelengths are the same, the difference between the two would be a whole integer multiple, so then you're going to get constructive interference. Does that make sense? It's basically measuring what part of the wave hits that specific detector screen point. And so what ends up happening is you'll get, yes, but if it was 10 and 10.5, then it would be destructive, correct? Does that make sense to everyone? If it's a whole integer multiple, it's constructive. It's a half integer off, it's destructive. It doesn't make sense. Okay, let's look at it graphically. If something came in and it had a certain wavelength and the other one was half off from it, so let's say this was your blue. Let's use that 10 and 10.5 example. So if it's 10.5, then this would have been the green. Right? So this was 10.5 and the blue was 10. This is what happens. This is what I'm talking about, what it being destructive. One is above, one is below. Remember that interference example that I gave way back when we talked about destructive interference, when part of the wave is above and versus the other one below? If it's slightly shifted, it wouldn't be perfectly destructive. It'll be slightly destructive instead of completely destructive. So you'll get gray instead of black. So half a wavelength off means that it's going to be completely destructive. Whole, you don't have to remember the equation. Just remember what I told you when we talked about. Look, so if this wave, okay, let's keep it the same notation. This was remember the example that I gave you guys, like this, and then the two waves approach each other, right? Except this green now is going to be inverted or half out of phase. Good Lord, sorry. So when they overlap, what happens? Nothing, right? Flat line. They cancel. Correct. Same thing's happening here, except if the distances, because these waves actually have to travel a certain distance. So if the distances that they travel are a half wavelength off, when they hit that detector screen, it will cancel out. There will be other parts on that detector screen where they add up. So on the detector screen, you'll have parts that are bright, dim, bright, dim. So where it's destructive, it'll be completely black. Where it's constructive, it'll be white on the detector screen. That's what you see on the detector screen as being white and being black. So black means what? Destructive interference. White means constructive interference. And somewhere in between, it'll be kind of grayish. Kind of like what someone mentioned it. Alexander mentioned it. Why isn't it like totally like it can be slightly shifted? Yeah, you can. It doesn't necessarily have to be. But what they're going to give you is the extreme cases, right? The destructive interference and the constructive interference. And this would be an application of those. So m is some integer multiple. And if it's a half integer multiple, then that's why you would go off. Oh, sure. Let's look at here. Where would it be gray? So at this point, it's completely black, right? So let's look at it. It's completely black here. Let me draw it. Here, 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 at these points. It'll also be black at the nodes too, right? Because nothing's happening there. In terms of brightness. But everywhere else in between, it's gray. Like if you think about it, this is gray. This is gray. 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 Does that make sense? If you think about it, if you have something that's completely positive and something that's completely negative, what's going to happen in terms of intensity of light? To cancel out, 0. So the lack of light is what? Black. Sorry, the question and one off just to be two identical waves right on top of each other, right? Yeah, so when the two identical waves are right on top of each other, then it's just the same wave, right? So this is if it was one off. Oh yeah, so that's what the one off means. So if they're one off, right, that green wave would be the blue wave. So if we're superimposing two waves on top of each other, then those waves would simply be additive. Oh, m, you don't have to worry about m. It's just some whole integer multiple away. So if we draw the distance, let's go back to the path length here. So let's draw this. So if this was 11 and this was 10, this is your path length here. This is where d sine theta is, right? Theta is here. This is d. D is here. So this is the path difference between the two, right? If we say take one, the blue one, and subtract from the green one, or the green one subtracted from the blue one, that difference is that d sine theta. That's your path difference. Yes, it'll be under light and optics. This will be under Young's double slit, and it's covered under light and optics. It's the last one in book 2, I believe. There might have been reorganized, but nope. Yeah, it's under light. It's a section 9, actually. It'll be under section 9. Geometric optics is the lenses and mirrors. That's section 10. So it'll be in section 9. Okay, for those who want to read about it. Any questions? There were questions. I just wanted to make sure if I clarified enough for everyone. So what M is, so if this was 0, so this would be M is 0, this is M is equal to 1. So it's 1 magnitude out, M is equal to 2, roughly from the center. That's what M is. So much that we can predict what the distance between these bright peaks are. Lambda is simply, or Y is simply lambda L divided by D. This is L, the length between the two double slit to where your detector screen is. And this is the equation associated with it. Okay. I know it's out of place, but ideally I would have done it there, but we might not actually have time for that class to discuss Young's double slit experiment. So that's why I wanted to go over it. And the key thing about Young's double slit experiment, because of the interference here, this shows that light has a wave nature. Okay. Any questions? Or any continuing questions? So here, this is the path length is a half wavelength off. Lambda is M plus 1/2. And then the other case was if it was the same, path length is lambda M, some integer, whole integer multiple. But we just over each other. So kind of like what I told you, they can give you that the blue distance was 10 lambda and the green one was 11 lambda. They're going to ask you, are we going to see a bright peak or a dark peak there? Correct. If the whole integer multiple off, then you're going to see constructive interference and you'll see a bright peak. Correct. Good job. You guys got it. No worries. We're all learning. We're all learning, Alexandra. We're all learning. I was like, I'd rather make my mistakes here now in front of, where I'm practicing. Because would you rather make it now or would you rather make it when you're taking the test when the scores actually count to get into med school? So I find no fault in missing it now, right? Because if we miss it now, it's like, all right, it's a correction of thought. I just go on and make sure that I understand why I miss it. Okay. Yeah, but this is a whole integer multiple off, right? So in this case, if it's a half integer multiple off, all where the blacks were would be black, right? However, when it's a whole integer multiple, it's a whole number that's multiplied to the wavelength. Because if you did 10 lambda minus 11 lambda, that's one whole lambda, right? That's a whole integer multiple. Then it'll be as if the waves are superimposed on each other. And we already know when one wave is superimposed on another wave that they simply add up, and the collective wave would be something like this, right? No, it just gets brighter. Oh, the name? This is path length or path difference. Which if we look at it on the picture here, I'll circle it in red for what that delta is. This is the difference. So if this was equal to this from this point onwards, then this is the difference between the green and the blue lengths to get to somewhere. Hence the name path length difference. Cool. Yeah, all those terms were like, what the hell are they talking about? Of course, there's black here where so black would occur at where the nodes are, right? Where the intensity of lights don't superimpose on each other. So you'll still have black for those types of waves. It'll just be here. Does that make sense? Yes, diffraction grating gives you the curvature or bent lights of rays of light coming out through the small opening, right? But it's interference that's giving you these bright and dark peaks. Yeah, so that's the difference. That's why for the first part of the graph over here, I called it diffraction, because diffraction is happening here and here. But over here, where the detector screen is, this is interference. And this is why light is behaving like a wave, because it can interfere with each other. Interference is a wave property. So diffraction, diffraction grating, those are putting a wavelength of light through a small opening, the opening being smaller than the wavelength itself. And it causes that bent nature of light to kind of like push through that small opening, going out like out in all directions. Does that make sense? Ha! Polarization is a totally different thing. So polarization is physical blocking of light. And it's blocking certain components of light, the electromagnetic and electric, or the magnetic part of the actual light wave. I can go over polarization during light and optics. It makes a lot more sense after I go over what an electric field is and what a magnetic field is, and how both light is comprised of both an electric field and a magnetic field. I don't want to scare you guys yet with waves that like are nonlinear. But a light wave itself has both a magnetic component and an electric component. But I only go over that after I go over electrostatics, electromagnetism. This one can stand on its own because it's still just talking about interference. It does, and the only thing I knew that I had to cover was diffraction, which I might not have time to do during the light and optics lecture. So, hence why it's going here. Great questions, guys. Any other questions? Cool. All right. With that, let's do some practice. Let's look at those in-class questions. Let's go. Number 1, what type of spot on the screen would be produced at a point 3.7 lambda from the upper slit and 4.2 from the lower slit in Young's double slit apparatus? Would it be a bright spot of maximum amplitude, a bright spot of reduced amplitude, a dark spot of 0 amplitude, or a gray spot of reduced amplitude? Sorry, I'm just checking. I'll go back. So if we look at our path differences, what's the difference between 3.7 lambda and 4.2 lambda? Sorry, I can't see all the keyboard typing. Yes, so it's half an integer or half a wavelength, so we know it has to be a dark spot. Destructive. Good. Number 2, for standing wave on a 0.5 meter string fixed at both ends, what wavelength corresponds to the third harmonic? This one should be pretty straightforward. Remember the wavelength equation? Lambda n is simply 2L over n. We have L and we have n, right? Because it's the third harmonic. Simply just plug it in. Lambda 3 is simply 2 times 1/2 times 3. This becomes 1/3 of a meter. Giving us answer choice. Awesome. People are feeling good. Get. So length is 1.2 meters, right? And we know lambda n is equal to 2L over n. That thickness is irrelevant because we don't need to know it. But if you don't know the equation, you probably would have tried to include that somewhere in there, right? So, which is not a possible, right? So lambda 1 would have been 2.4 divided by 1. Lambda 2 would have been 2.4 divided by 2. Lambda 3 would have been 2.4 divided by 3, right? So 1 is 2.4, so that works. 2.4 divided by 2 is 1.2. This is going to be 2.4, that's going to be 0.8. So this was 1.2, this was 2.4. So we already know what doesn't fit. We can do the fourth one. That's 2.4 divided by 4, which is 0.6. So that checks as well. Check, check, and check. So there's only one that doesn't fit. 0.9. Yes, you need to remember. Sorry, I was asked to go back 1 second. My bad. So let's go back to the previous question for number 2. I'm going to zoom out so you can see both. So far, so good. C was the correct answer for number 2. And for number 1, it was a dark spot. Right? Awesome. Everyone's good. Look at that. Teaching theory first helps a lot. Which of the following wavelengths does not correspond to the electromagnetic radiation listed? UV, 317 nanometers. Ultraviolet visible light is 426 nanometers. Infrared is 712.21 angstroms. And the X-rays are 211 picometers. Right, to determine the magnitude, we just take the speed of light divided by whatever the frequency was for each one of the systems, right? So the only one that doesn't work, if you think about it, it's 3 times 10 to the 8th divided by each one of these frequencies that you had. But the one that doesn't work, which is around 10 to the 14th, so that should be 3 times 10 to the negative 6, roughly, for infrared. Angstroms is 10 to the negative 10th. Okay. And with that, we're done. Can you explain the zero amplitude part of 1? Yes. So if it's a half integer multiple, it's destructive from what we talked about for Young's double slit. So let's go back on this diagram and we scroll up. Within your handout, you had your Young's double slit experiment right here. So if it's a whole integer multiple, then it's in phase or constructive interference. If it's a half integer multiple, then it's destructive. Right here. Does that make sense?
Your screen share's off.
Oh, my bad.
You're fine.
Sorry. I stopped screen share and I thought I was still on screen share. Here you go. Thanks for letting me know. So what I highlighted was if it's a half integer multiple off, then it's destructive. If it's a whole, it's constructive. Constructives in red, destructives in green, or I guess I should have did black, but that doesn't do too well when I highlight in black. Does that make sense? Question 5, you don't know the answer because we haven't gone over the things to do it. And it makes sense to do reflection and refraction when I do light and optics. Because when I go over the geometric devices for light and optics, the lenses and mirrors, we're going to have to go over reflection and refraction then too. Okay. And so that's why, so you should know how to do the question 5. Okay. Because that has to deal with thin film interference, and you have to understand. Well, 10 times 10 to the negative 10th is the same thing as 1 times 10 to the negative 10th. Because 1 times anything is just itself. Ha Harmonics is only when we're talking about tubes and pipes and stuff. But when the open pipe system and the closed pipe system, but when we're talking about standing waves, so someone said that they noticed part of today's lectures was harmonics, which was in the sound lecture, and that they have to read that part. You have to just to understand what a harmonic is for what those standing waves were, but it should have been in your periodic motion and waves also. The homework tonight is your waves section, right? This should be in your book. It should be under periodic motion still. There should be periodic motion and waves. But yeah, it should be periodic motion. It should be under there. Yeah, and I think the handout also tells you what the homework is too, right? So here is the homework following the lecture. Periodic motion and waves, book 1, page 159, review questions, and then book 2, light and radiation, which is only when we're dealing with your Young's double slit stuff. Okay. Anything else we'll cover during the light and optics lecture. Cool. Yes, to find the path length or the path length difference, we take the difference between the upper slit and the lower slit to get to that point, the distance. Correct. And then the difference would then tell you if it's destructive or constructive. Correct. But all the handouts when we're doing those things usually have a pretty good what you should do before, right? So all your handout for every lecture that we have has a what do you need to do before. Yeah, just those sections, yes. That's listed in the handout. Cool. All right, guys, it's 4. I have another meeting I have to go to. You guys enjoy the rest of your Monday, and then we'll talk about acidic and basic relationships on Wednesday. And we'll compare it to all those high school relationships you used to see. Number 4? Yes. So for number 4, I think I'm still sharing screen, right?